All right. So this section deals with what's called the disk method. In fact, we're going to do disk method, and then we're going to do tomorrow what's called washer method. And they're really the same methods. It's just conceptually, think of a disk like a quarter or something that is solid all the way through. And then think of a washer, simply like what's on the picture of your calculus book. There's a hole in the center. And so they're basically the same method, but you have to subtract out the hole pretty much when you do the second method. But the disk method and then the washer method is what the second one is called. And so they give you a picture of what some of these figures would look like. And they give you all sorts of figures that have been rotated. What they're actually doing is they're taking this function here, right? And they are taking a piece of it and they're rotating it. Rotating it around at first an axis, and then we're going to rotate it around other things as well. And so if you were to try to calculate this volume, you would take pi r squared, like the volume of a circle, times the height. So think of just a cylinder, when you did a cylinder way back in geometry. And so when you calculated a cylinder, it would look something like this, right? These two guys here, you would calculate the area of the base times the height, right? That's what you would do to do a cylinder. And so when you think about this, that's basically what they've given you. They've given you pi r squared times w. R squared now, though, however, is represented by a function. It's no longer just a dimension. It is now a function. And so if you look at the next page, they give you some more representative drawings here. They go back to the concept of rectangles, because that's what you can visualize. And if they were to take each one of these rectangles and rotate it, you would get this volume produced. And so all of a sudden, your width is now how much the x is changing. Change in x, delta x. That's the width of this guy. Your radius of it is still represented by whatever function you've been given. So anywhere on this function is going to be the radius of that particular disk, right? And then you have a width, depending on if they want from 0 to 1 or 0 to 2, or however big they want it, they will give you that information or information to be able to solve for that. And so this is where we get the information that they have on this page here, on page 422. Known pre-calculus formula is pi r squared w, or pi r squared height, if you were to do it from like a perspective of a cylinder. Now, if we were to change that out with function notation here, then you would say, well, we're talking about a radius being a function. So the radius function squared. And instead of your height or your width, we're talking about change in x, delta x. And so when we revolve it with integration, we're talking about from point A to point B. Pi, that is just a constant. So pi is hanging out here on the outside of your integration, because it's just like if you were multiplying by 2. It's pi. Your function squared, dx is the representation of your delta x, your change in x. And so this is where we get the formula. Horizontal axis of revolution. So horizontal meaning just what it means. If it is y equals 0, the x-axis, or any parallel to the x-axis, you're going to use it in terms of x. If you were doing a vertical revolution, so now think of vertical y-axis or anything parallel to the y-axis, you are going to write this function in terms of y. But the formula is the same. Pi times r squared, meaning the function squared, times either dx or dy, depending on what terms you have it in. We're going to look at another video, but what we just looked at was around the x-axis. So if you were to take it and revolve it, it can be revolved around the y-axis, and they've given you this example here. Vertical axis is what I was talking about. So we're going to watch what he does with a vertical axis, but those are in terms of y. So instead of y equals x something, it's going to be x equals y something. So in terms of y is really the only difference. So let's look at this first example here on page 423. So it says, find the volume of the solid formed by revolving the region abounded by the graph f of x equals square root of sine of x and the x-axis from 0 to pi about the x-axis. So we are bounded by the x-axis and we are revolving around the x-axis. That's important because we're going to start laying a foundation for how to do ones that aren't bounded by what you're revolving around. In this case, it's bounded by this function and the x-axis, meaning The function itself creates a boundary, and the axis creates a boundary. And then they want us to revolve it around the x-axis. And they want us to go from 0 to pi. All right, and when you revolve it, you see it looks somewhat like this. So you will have these individual discs that are created all along here. All right, and so we are revolving around one of our boundaries. Revolving around one of our boundaries. Specifically, it is a horizontal boundary. So it has to be in terms of x, which it is. All right. It butts right up next to our boundary, so there's not going to be any type of gap or any type of movement that we need to worry about. And it's an axis, meaning our function itself is right up next to, it's going straight from the axis to the function. All right. And so these are all key features that we need to pay attention to. And so for this one, we're going to use our standard formula. We're going to use the one that it gave us over here, where it's just the volume is going to be equal to pi from the top and bottom here, which they've given us, of our function squared dx. And so we're just going to plug that stuff in. We're going to say from 0 to pi is what they gave us. So we're going to go from 0 to pi, all right? And then our function is the square root of sine. So we're going to say the square root of sine of x squared dx, all right? And then we're just going to analyze it. So for the first thing you want to do is you want to obviously square the function first. So sine, the square root of sine squared is just sine. So we end up with sine of x dx. The antiderivative of sine of x is negative cosine of x. So we have pi negative cosine of x from 0 to pi. All right, and then we just plug it in. So if you plug in a pi here, and I'm going to actually do it this way, negative cosine of pi minus negative cosine of 0. Pay attention to your positives and negatives here. Cosine of pi is -1, right? So negative 1 ends up being 1. And then cosine of 0 is +1, so you end up with minus a -1. So your answer here ends up being 2 pi. We are going to take from 0 to 1, right? Because they've given us those boundaries here. And then we're going to say pi. We are revolving around the x-axis, which is what we're bounded by according to this, right? So we're going to take our function, negative x plus 1, and we're going to square it, dx. And so then we need to square the function, which means you need to FOIL it, right? Negative x times negative x is x squared, minus 2x plus 1 is what that looks like when you square it. And then 0 to 1. And dx. And then we're going to take the antiderivative of this. So we have pi x cubed over 3 minus x squared plus x from 0 to 1. Plug in a 1. You get 1/3 minus 1 plus 1. And then, of course, if you plug in a 0, it's just minus 0, so that's not going to do anything. This ends up being 1/3 times pi, or pi over 3. That's actually all I planned, so you're good. Yeah. So in this, it says, find the volume of the solid formed by revolving the region bounded by f of x equals 2x minus x squared and g of x equals 1. Those are the boundaries. The boundaries are the function and the line y equals 1. And we want to revolve it around the line y equals 1. So one of my boundaries and what I'm revolving around are the same thing. I keep saying that because that is important when we move to washer method. So that means that I am no longer revolving around an axis, but I am revolving around a boundary. There will be no gap between my function and what I'm revolving around. So in this case, I need to subtract these. that means the radius then that I am squaring. So normally I would just do my function squared, right? So I would say, normally I would say pi out here, my r of x squared, right? Dx. But now this radius that is created is no longer just my function. It is my function minus the line. It's the difference between the two, okay? And so I'm going to say, well, it's going to be 2 minus x squared minus 1. Because this is my function, and this is the line I'm revolving it around. And that is what my radius will be. So my radius ends up being 1 minus x squared. That is what I will use to throw into this equation.
So everything else is...
In this case, we are going from -1 to +1. We know that because that's where they intersect. So if I were to, that's the next step. But we're going to say 2 minus x squared equals 1. And if we solve for that, you'll get x squared equals 1. So we're going to go from -1 to +1 here. There are going to be cases where what you're revolving around is above it. And so you would do the opposite. You would say the line minus the function. You still have to consider what you're revolving, because if you did it the other way, it would be backwards. So in this case, the function itself is above what we're revolving around. If I were to plug in a 0, because we're going from like -1 here to 1. If I were to plug in a 0 into these, you could see the function is above the line you're revolving around. So you're going to subtract that way. There are going to be times when you subtract the other direction. And so now we're going to fill that in. We're going to fill in this, the 1 minus x squared. And we're going to square that dx. So you want to square it before you take your antiderivative. So this is going to end up being 1 minus 2x squared plus x to the 4th dx, that whole thing. And then we'll take the antiderivative. All right, and then just plug it in. So plug in your 1, and I'm just going to put it up here. Pi. When we plug in a 1, we get 1 minus 2/3 plus 1/5. Minus, when we plug in a -1, we get -1 plus 2/3 minus 1/5. And so distribute that negative, you get 1 plus 1. -2/3 minus 2/3, and then 1/5 plus 1/5. And your common denominator here is 15. So you end up with 30 over 15 minus 20 over 15 plus 6 over 15. So you get 16 pi over 15. They've given us these boundaries. Let me see exactly how they worded it.
Wait, what was the answer to the first?
So in this particular situation, and we're actually going to come back to this when we do the washer method. In this particular situation, you are looking at what they've given you here. They've given you y equals 2x squared, y equals 0, x equals 2. And now they want it around the y-axis. They actually started with the y-axis, which may have thrown you off a little bit. Because the x-axis is kind of our default, and the x-axis we could have left it the way they gave it to us. But in this case, they wanted it around the y-axis, so we actually had to write it in terms of y. And so your first step would be to rewrite these guys in terms of y. And so I am going to take the original that they gave me here, and I'm going to write that in terms of y being my variable, my dependent variable. And so, or my independent variable rather. So I'm going to say, instead of y equals 2x squared, I'm going to say x equals the square root of y over 2. So I'm going to actually solve for x. Boundaries here. So I know one of my boundaries is 0 because they told me y equals 0. My other boundary is what happens at my other y. I know where x is, so I just plug it in. 2 squared times 2, right? Which would give me 8. So I have an upper boundary here of 8.
Hey,
My boundaries need to be in terms of y as well. They gave me one of them, y equals 0. My other one was in terms of x. So I need that x in terms of y. So I just plug it in. So I just plugged it in right here. 2 squared times 2 is 8. So my other y would be 8.
Okay.
And then I'm going to use, this is my function, squared dy. And then just to simplify, obviously when you square the square root, you get y over 2. And I actually pulled the 1/2 out. So I have pi over 2 out here and just a y. Because I squared this to get y over 2. And then I just pulled that 1/2 out. You don't have to, but that's how I did it. And then when you actually take the antiderivative here, you get pi over 2. The antiderivative of this is 1/2 y squared. And we're going from 0 to 8. So you get, when you plug in an 8, you get 64 pi over 4, which is how you get 16 pi. So for the next one, we have the x-axis, which is kind of what we were used to doing a little bit more than the y-axis. So we are going to leave it, I pushed it up there a little too much. We're going to leave it in terms of y. So we just have y equals 2x squared. That's what we're going to use for this one. 2x squared. We have our pi here. We know when y is 0, so we're going to have to put this in terms of x. So when y is 0, x is also 0. And then they gave me the other x of 2. So again, I'm going to simplify and then take my antiderivative here. 4x to the 4th. Antiderivative of that is 4/5 x to the 5th from 0 to 2. Plug in a 2, you get 32. 32 times 4 is 128. For this one, they want the line at x equals 2. And we're going to talk today about how to distinguish between this. We go from 0 to 2 on the x-axis. So I know that my graph is going to go from 0 to 2. They want me to revolve around this particular one. And this is a parabola. How do I know it's a parabola? Y equals 2x squared.
X squared.
Right. So in this particular case, I have some sort of parabola going here. So I have no gap between this line and my function. All right. The function actually is determined at 2. There's no issues with what happens at the function. I'm not looking at a secondary function that might create a gap. And so this border is butted up to my particular function itself. And so I need to know which one goes first, pretty much, but that's about it. I also need to think about which one I'm doing. The line x equals 2 is parallel to which axis? X equals 2 is parallel to the y-axis. So I'm going to use the same setup that I used up here in the first one when I did the y-axis rotation, which means I'm going to have to use this function. So I'm going to look between the function x equals 2 and x equals square root of y over 2. And I'm going to go from 0 to 8 because it's the same determination here. And so once I've decided that, I just need to decide which one's first and which one's second. And in this case, 2, between 2 and square root of y over 2, I can pick any number, really, between 0 and 8, and I am going to get that 2's bigger. Because even if I plug in an 8 over 2 is 4, the square root of 4 is 2. If I go below that, 7 halves, the square root of 7 halves is going to be smaller than 2. And so I'm going to actually plug it in with the 2 first, the square root of y over 2 second, dy. And I'm actually going to take this guy to a second page so y'all can see it. Only algebraically is this more work. calculus wise, I mean, we're pretty much done as far as once you have the setup. You just have to do the algebra piece and take the antiderivative. But the algebra piece is a little more difficult. So the first thing you want to do is you want to simplify the function itself before you actually take that antiderivative. And so I'm going to FOIL this. That should be a 4. There's 2 of those. And then now I'm ready to take my antiderivative. The antiderivative is in no way pretty, but so I rewrote this as 4 over the square root of 2 times the square root of y, because that's just a coefficient. So if you simplify 4 over the square root of 2, that's fine. I mean, it's going to be 2 square root of 2, because you end up with top and bottom by square root of 2. You end up with 4 square root of 2 over 2. And then so you end up with 2 square root of 2 here. So I just simplified my fraction there. And then y to the 1/2 you add, right? Which is 3/2, and then you multiply by the reciprocal. So we're going to multiply this by 2/3. So this is 2/3 y to the 3/2 is what happens with that. And then, of course, this is 1/2 times y. So I end up with 1/2 times y squared over 2 as my antiderivative of that one. And I'm going from 0 to 8. I'll make this prettier, but I was just showing my process here. So we have 4y minus 4 square root of 2 over 3, y to the 3/2, plus 1/4 y squared from 0 to 8. It's easy when we plug in an 8 to the first and last one. 8 and 4 gives us 32. 64 over 4 over here is going to give us 16. This guy right here, so 3/2, 8 to the 3/2 is the square root of 8 cubed. The square root of 8 is 2 square root of 2. Okay, so when you cube 2 square root of 2, right, you end up with like, how to explain this? So I end up with having lots of square root of 2's here. So 2 cubed, of course, is 8. Then I end up with square root of 2 times square root of 2 times square root of 2 times square root of 2. So I end up with 4 square root of 2's, which is 2 2's, right? So I end up with a 4 there, if that makes any sense whatsoever. The truth is, at this point, even if you don't want to do that part of the process, you can plug in an 8. So if you plug in an 8 right here, plug in an 8 right here. If you plug in an 8 right there, you end up with, I got 128 over 3. So you end up with 128 over 3. You can plug in your 8 and you're going to get it. I mean, that's what you're going to get there. When you multiply 4 times the square root of 2 times 8 to the 3/2. And then if you get a common denominator here, you're going to end up with 16/3. So we have been dealing with things that have butted right up to my boundaries. And when that happens, it's great. You have this solid disk. There's a reason this is called the washer method. In fact, some books don't separate these methods at all. They actually push them together as one method, because you're basically just doing the washer method twice, okay? I mean, the disk method twice to do the washer method. Because basically what you do to solve this guy is you solve the disk all the way to the center. So your largest radius, you solve that one first. And then you subtract out the smaller one. So you basically take the whole disk and subtract the whole. Subtract the entire disk and subtract the whole of it, all right? Think of a donut, right? Because it's right before lunch. So you would take the donut before the hole's in it and then subtract the piece of the hole, and you would get the actual volume of the donut itself. And that's what we're doing with this. And so it's technically just the disk method done twice. So in lieu of when we had a line and I put the line inside of it. So this last one we just did, I put the line that I'm revolving around inside of the function that I squared. That became my new function because I butted right up to it and there was no hole. And so I was just calculating, instead of from the axis to my function, think of it as a new axis to the function. And that's why I did 8 minus my function, all right, as my new function itself, or 4 minus, or whatever line it was. And so in this case, I actually have two functions because I've created this hole. And so I calculate my large function and subtract the hole itself. And so because there's a gap, you have to do it separately. If there is no gap, you actually throw it in there and that's your new function. But there's a gap, so we're going to do two functions. And it's basically the first function squared minus the second function squared, instead of throwing the line within it and creating a new one. So, change. So the first thing we did here, I'm going to highlight it so it's in a little bit of a different color. The first thing we did is we set the two functions equal to each other, and we figured out where they intersect. Those are my boundaries from 0 to 1. And then after that, I had to decide which one was furthest away from what I am revolving around. I'm revolving around my x-axis. And so I determined that my square root of x was further away, so that's my outside radius, and my x squared was closer, that's my inside radius. And now I'm just going to square them and then take the antiderivative of them.
Oh, so you determine.
And then I'm just going to do the math here. So I'm going to go from 0 to 1. This is going to become x. This is going to become x to the 4th. Then I'm going to go ahead and take my antiderivative here. We're going to go from 0 to 1. When you plug in a 1 there, you end up with just 1/2 minus 1/5 for your 1. When you plug in a 0, of course, you get 0 minus 0. The common denominator here is 10, so you end up with 5/10 minus 3/10, or minus 2/10, right? Which gives you 3/10 multiplied by pi, of course, 3 pi over 10. And revolve around that line. What's my outer radius going to be? 8. Do you see why? Because from 0 to 8, that's my outer radius. If I were to revolve that entire thing, I'd have a huge disk with a radius of 8. So that's my outer radius. My outer radius here is just 8. Okay? Now my inner radius is going to be not just this function, because I'm no longer revolving around the x-axis. I actually need the gap. I need the gap between the function 8 and the function 2x squared. So how do I get that gap?
You subtract function 8 from 2x squared.
Correct. Well, vice versa. 8 minus the function, right? 8 minus the function. Does that make sense? Because I'm revolving this way up, not down. So to get my inner radius, my little r is what I'm looking for, I have to take that highest one and subtract.
Why does the 8 go first?
Because it is closer to, it is creating the gap between. So, if I were to do the other one subtracted from 8, I would get a negative there. Like, if I were to take this function and subtract the 8, it'd be going the opposite direction. So you have to think about the fact you're revolving around this, and you're trying to get this piece of it, the area under it, revolved, not the area in between. You're actually subtracting out the area in between. So I need to see the difference between this function and my parabola. So I need to take this function minus the parabola and subtract it from the entire disk itself, and I will get this piece right here, which is what I'm actually trying to get. This piece right here revolved. That's what I'm trying to revolve. So I have to take, basically have to take this whole part here revolved and subtract out the gap right here to get this little leftover piece. So I'm taking 8, that's my function, that's going to give me the huge disk. Subtract out the 8 minus the parabola, this hole right here, and I'll get what's left over from the 8. And so those are what I'm actually plugging in to my squared. R squared, capital R minus little r, pretty much. So that's what I'm going to do here. I'm still going to do from 0 to 2, the same way I would have set up, because I'm doing it in terms of x, right? So I'm still going to go from 0 to 2, because those are the limits that I have on my x's. 0 to 2 is still going to be there. My first function is just going to be 8 squared. My second function is going to be 8 minus 2x squared squared. And that's what that's going to look like, that setup. The setup is by far the hardest part of these. And then just do the algebra. Simplify first and then do antiderivative. So we have 64. Remember that's a subtraction there. So 64 minus 32x squared plus 4x to the 4th. dx. And you can simplify this by distributing that negative. So you end up, these 64s end up canceling. This is minus a negative. So that ends up being a positive 32 and a negative 4x squared. So when I take the antiderivative, that's going to become 32 over 3, new exponent, x cubed, plus 4/5 x to the 5th. And we're going to go from 0 to 2. And you get a huge when you plug that in, because you get 256 when you do 8 times 32, and you get 128 when you, so when we plug this in, we're going to get 256 over 3 minus 128 over 5. A common denominator of 15 gives you a rather large fraction here. So in this particular case, we have the function y equals x squared plus 1, y equals 0, x equals 0, and x equals 1, and they want us to revolve it around the y-axis. You actually have two shapes that are created here. So two things happen. It's almost like a piecewise function. Remember those from, way back when you had, okay, from here to here, this is the function, and then from here to here, this is the function. And that's kind of what happens here. When I'm revolving around the y-axis, if you were to look at these particular functions, from 0 to 1, they gave me my x's, and they gave me basically my y's. If I were to plug in a 1 for my x, I have 0 to 2 for my y. So I know my x limitations are 0 to 1, my y's are 0 to 2, because if I plug in a 0 here, I get 1. If I plug in a 1 here, I get 2. But they've already told me y goes all the way to 0, okay? But my x limitation of 0 gives me a higher value than 0. Does everybody see that? So I actually cross the y-axis higher than what it told me to based on just my limitations. And so from 0 to 1 for y, I have this perfect little solid here. The perfect little solid is created by x equals 1 and x equals 0. Those are my two functions, my inner and outer functions here. And if you look at how it's set up in your book, those are your inner and outer functions. Your 1 squared is your outer function. Your 0 squared is your inner function, because this is created. 1 is my outer, it's the furthest from the y-axis. 0 is my inner, it is the y-axis. So those are my inner and outer from 0 to 1 for y. But from 1 to 2, something else happens. My outer is still my x equals 1, right? My inner is now my x equals square root of y minus 1 when I put this in terms of x. And so I end up with two different integrations because the limits that they gave me say something different than when I plug in my x's and y's here. And so it told me, no, I want you to go all the way to 0 for y, even though your x's stay exactly the same for that whole thing up until you get to this 1. And so you have to kind of consider that there's two things happening with this function and set it up as two different options here. And that's exactly how you solve this one. You have two functions. You end up with the first one from 0 to 1, and this is the outer function, 1 squared, and this is the inner function, 0 squared. And then you add to that what happens from 1 to 2. So from 1 to 2, this is again my outer function, but my inner function is this in terms of y. So we end up with square root of y minus 1 squared. And so you have two different things happening because of the way this one crosses the y-axis. And it would not be that way if they had said the x-axis. The x-axis would have been much more simple. We would have gone from 0 to 1, and this was just a disk method. This would have been my outer function squared. So y-axis is much more difficult in this particular situation than an x-axis revolution. X-axis revolution would have been a straight, simple, from 0 to 1, my function squared, dx. Because there is no gap and there is no inner and outer function. It is a disk, a true disk. But you create a disk and a washer when you do it around the y-axis. So it's two different things. Okay, so when you set this one up, set them equal to each other to figure out your boundaries, 0 to 2. Your outer is going to be your 4x minus x squared, because if you plug in a 1, you'll see your y value for this one is bigger. So this is further away from the x-axis. This is closer. All right. Then you're going to set them up, use your algebra. This is just squaring, simplifying, and taking the antiderivative and plugging it in. Let me quickly show you the next one. Line y equals x is different. So for line y equals x, when you set up your r, your boundaries are going to be the same, 0 to 2, upper and lower boundaries. But when you set up your large r and your smaller r, you have to consider that you are now talking about x equals, or y equals 6. Y equals 6 is way up here. This is going to be where we're revolving around. And so earlier, my lowest one was the x squared. That's actually going to be my bigger radius this time. 6 minus my x squared is going to be my bigger radius from this line all the way down to my x squared, because my x squared was closest to the x-axis, remember? And then my inner radius is going to be 6 minus my 4x minus x squared. It's going to be that one. So my one furthest away from my line is going to be this one. My one closest to my line is going to be that one. And so they're going to look completely different than the other one. And so sometimes figuring out what's closest to the x-axis will help you for the next piece of it, because the 6 is further away from the x-axis. So now we're talking about what's further away from the 6, not the x-axis. And because my x squared was closest to my x-axis, is actually further away from my 6. So that becomes my outer radius. And the one further away from the x-axis is actually closer to the 6, and that becomes my inner radius. And so you end up with outer inner that looks like these right here. So to finish out 13b, we said that the larger radius is going to be 6 minus x squared, because if you'll recall, on the unit circle, the x squared was actually closer to the x-axis from 0 to 2. And then that would mean that it would be farther away from the line y equals 6, which is what we're revolving around. And so we would take the 6 minus the x squared to get the outer radius. And the inner radius is actually going to be our 4x minus x squared. So we would say 6 minus 4x minus x squared for our inner radius. And you can simplify that by distributing the negative. You end up with x squared minus 4x minus 6 when you simplify that, because that one is actually going to be closer to the line that we are revolving around. So that's going to be our inner. And so to set this one up, we would still be going from 0 to 2 for pi. Our first function would be our outer radius, 6 minus x squared, squared. Our second function would be our inner radius, x squared minus 4x minus 6, rather plus 6 squared dx. Go ahead and FOIL these. You end up with 36 minus 12x squared plus x to the 4th minus, FOIL this one as well, x to the 4th minus 8x cubed plus 28x squared minus 48x plus 36. And you can simplify these. You can see your 36 and your 36 will cancel. You have an x to the 4th that will also cancel. You are subtracting here, so minus a negative 8x cubed is a positive 8x cubed. Minus a 28x squared and a positive, or minus a 12x squared and minus a 28x squared is where we're going to get our negative 40x squared. And then we have minus a negative 48x, which gives us a positive 48x. And so that makes it a little more simple when we are taking our antiderivative here. The antiderivative is then going to be 8x to the 4th over 4 minus 40x cubed over 3 plus 48x squared over 2 from 0 to 2. And when you plug all of that in, you will end up with 32 minus 320 over 3 plus 96. When you get a common denominator and simplify, that is 64 pi over 3. And that is your final answer there.